Yes.
Oh, yeah, works. Okay. Okay, good. Okay, so I start my speech. Is it okay? And occasionally I'm going to ask you to tell me if you actually fall asleep or you're still with me. Is it okay? All right. So you said last time you want full screen. Let me do full screen. Here we go. And I take the pen, or not yet. All right. So we are in the section about hydrostatic. And we developed the equations. And this chapter is basically showing how the pressure is varying with depth. So we developed this formula. But the more important part is actually look at the forces due to pressure, which will come later on. Then as a starter, we looked at accelerating containers. And the first case was the little container like a fish tank, which is shown in the bottom here, right here. Let me get the pen. Like here, this is this case. And if it accelerates to the right, the fluid probably going to assume a different shape. And we stressed it that it is stationary, although the whole system is accelerating. So the fluid particles are not moving, therefore disqualify as hydrostatic. Now, if we agree on all that, then what is happening is we would like to find out what is the pressure inside the fluid at any point, and what is the shape of the interface or the surface of the water. And then we did some algebra and did solve that case. And of course, the next case is going to be radial acceleration in a spinning container. So that's the next one we're going to do. Again, at the end of that case, which was the previous class, we showed that the simple formula is that the pressure increases with rho GH is working in this case as well. But now you have to know what is the shape of the upper surface. So this is how we started, just refreshing your memory. So this is the new material. Okay, so we'll continue. And again, there's a container which is cylindrical. Let me grab the pen. So here's a container which is cylindrical right here. This is a cylindrical container. And it is spinning around the z-axis. Note the way we put the coordinate system. The coordinate system is placed at the bottom. So here's the origin. And r is the radial distance, and z is the height. And of course, it spins about the z-axis. And so now we need to write down, we do exactly the same thing, write down the equations the same way we did before. So remember, we had rho A equal gradient P and minus G. But here I just left the formula the way it was in a vector form. We're looking at what the body force, we call the body force acting only to the minus G direction, okay, minus Z direction. Now, we go back to good old dynamics, and if there is an acceleration, okay, if there is a cylindrical surface and it is spinning, then here's a particle, and then as it goes, it's forced to go inward. So it has an acceleration inside, but we measure the radius outside. This is r. Therefore, the acceleration is going to be r omega squared, which is inward. Okay, so that's what we said. That's the acceleration. So now the coordinate system is going to be r, theta, and z. So the coordinate system is r, theta, tangential, and z. We think that nothing happens tangentially, so we're not really looking at very much, but we still write down all the equation in a vector form. So this equation in vector form will look like that, okay? So acceleration to the radial direction is kind of balanced by the pressure to that direction. The pressure to the vertical is the same here, but on the tangential coordinate system, nothing is happening. So the pressure is probably going to be constant once we integrate it. This is exactly how we started. The only difference is before this, this was actually x, and this was equal to 0. So now we're adding another term into the g, which is this one. We're very, very similar, actually very, very similar. So, okay. And of course, we're going to ask the same questions. What would be the pressure at an arbitrary point here? What is the shape of that surface? And then we're going to have another question is, suppose this is the current shape of the liquid. How was the initial condition before it started spinning? So this will represent the line. We'll go back to that again. So these are the questions. Hopefully you understand the problem. Very, very simple. Okay. And I always mention that you don't go to Home Depot and then they give you the paint and then they're spinning it in order to mix it. And there is something like that is happening, although the fluid is very viscous, but still it happens the same thing. And at the end of the day, the particles in the fluid are not moving, so we end up with a steady state condition. Okay, so remember those three equations. So we integrate the radial direction, and this is rho r omega, that was the acceleration. We integrate it, so it's going to be r, and then we have, of course, r here. Let me get the pen before I mess it up again. So we have r here, and then we integrate with r, so we end up with r squared. So now we put it in the, and then we have a constant of integration. To the tangential direction, as I said, nothing happens, it's constant. And PZ is exactly what we had before. So we combine these two results, and then we assume that this constant represent C1 plus C2 plus C3, and we end up with this formula. So this will represent the pressure inside. If you would like to find out what is the value of C, which is going to be determined by some initial conditions. So we're looking at the model, and then we claim that probably while it is spinning, there is a minimum distance. Let me go back here. So we're going to call that distance minimum. So we think there's a minimum distance here, Z minimum. And this point at Z minimum, we think that the pressure is equal to PA because it's on the interface, on the surface. So if we put in this boundary condition, okay, let's go back. Okay, the boundary condition is that at Z equals Z minimum, pressure is equal to PA. We put that condition into this equation, okay? So P at R equals 0, which is the center, and at Z equal minimum, equal that. And then we plug in the coordinates. R is 0, so this term becomes 0. This is 0 because of that. And then minus GZ, and Z becomes minimum. We still have the C from here. Algebra, we find out this is C. Now we have to resubstitute this C into that equation. And let's see what happens. Of course, it's going to look very simple. And here we go, and turns out that this is it. This is the final formula for the pressure inside the container. Okay, so one more time. We have a container, it is spinning. Okay, it is spinning as a shape. This formula is good anywhere here, any point here inside. Then would be nice to figure out what is the shape of that interface, okay? So it should be included in this formula. So what we're gonna do is we're gonna say that the pressure in this surface is equal to PA, and therefore we end up with this here. That is 0 equal to that. We have to solve for Z, which is a function of R, to get the shape of the curve. And this equation has it, and then just redoing it, just doing the algebra, we end up with Z equals Z minimum. So this is Z minimum. And then from here on, it's a parabola going with the square of the radius, which is R, or the radial distance. So Very, very simple, divided by 2g, and that's what it is. Now, okay, so we answered the second question. We had the first question, what is the pressure inside? This is one. And then what is the shape of the surface? This is two. And then I added one more thing, and I said, would be nice to figure out how this relates to the initial condition when the fluid is level and the container is not spinning. So we need to do a little bit of algebra. So for example, what we can say is that the amount of liquid is the same before the spinning started and after. So that's what we say here. Let me just, so that's what we claim, that has to be the same. So what is the volume before? So it's the base, pi r square, capital R, because that's the capital R represents the radius of the container, while the little r, it represents the coordinate, okay? Some student asked that question. And then Z0 is the height. So one more time, here's the container. There's an average velocity here, some height here, initial height. We call that one Z0. And the volume, of course, is base times the base, which is pi r square. This is capital R. And multiplied by so that's the volume, no rocket science here. Now we need to figure out what's the volume after. So the volume after, the Z, or the height of the liquid, is actually changing. So we need to take the Z, the height of the liquid, multiplied by 2 pi r dr, and that would be the volume. Now, let me just, for the people who don't like too much math. So I take a segment here. And then the thickness of the segment is dr. dr because the radius goes this way. This is r. This is the r coordinate. And this segment is right here. So I'm trying to figure out what's the volume of this segment here. So the volume of this segment is the local z, and 2 pi r, which is around the circle, and then dr, which is the thickness of that strip, Okay, so then z, we have the formula for z from before, and the z is going to be equal to this quantity. Let's go back to the previous slide. Remember, we developed this formula. We have the formula here, which shows the shape. This is the shape of the surface. So we have the height. It's no problem. So we just use that formula. We go back, and that's what we did. We substituted that way here, right here. There it is. That's the z. And then we just do the integral. So integral, the first one is a number, and this is going to be 2 pi r, and integrate, and between the limits of capital R and 0, 0 is nothing, so we put here capital R. It's going to be r squared because R and R. Okay, so that was very easy. And then the second term, of course, is going to be this. And now we have R and R, which is the third. And then we have to multiply it it's going to be R to the 4 divided by 4. Okay, so and then we have the 2g, and then we have the 2 here, the 2 and 2 cancels out. Anyway, that's the final result. Okay, now then we have to compare the two volumes. So we compare this one, which we integrated, to the one. And why are we doing that? Because we're trying to figure out how Z0 relates to, say, what is here. Here we have Z minimum. What's the relation between the two? Okay, so I compare the two, okay? And then just algebra, trying to solve for Z0. Okay, solve Z0, just divide by pi r squared. So we got Z minimum and this quantity, okay? So now we go back and we're trying to see what happened before. Okay, so let me just go back. Where's the formula? Or I can actually say this. If you look at this formula, this is actually equal to Z, correct? And then Z max, the maximum Z, is going to be when this R is equal to capital R at the brim, at the diameter of the thing. So, and then that equation is exactly, that's it. This is that one, Z minimum. Now, what we did here turns out that the average place is Z0, Z minimum. And this is 4, and this is 2. So all the experts in algebra can see exactly what happened. This is that. First of all, this is a parabola, as we said. This is a parabola. And this is the initial volume, which is Z0. This is the maximum, Z max. And this is Z minimum. And this height is exactly in the middle. It bisects the two distances. So we can simply write it, which is, I like it more this way. And that, let's say Z0, so Z minimum will go down, while Z maximum will go up by the same amount, which is R omega square over 4G. Okay? So that's the algebra. Basically answered all three questions. What is the pressure at any point? And what is the shape of the interface? And what would be the height of the liquid before the spinning started? Okay, very, very simple. If you have no objection, we can continue and do some example. Okay. So, before I go to the example, I said actually one more thing. So in the previous case, I showed you that we can actually use the simple formula, but you need to know the shape of the interface. So what is a simple formula? If I find a point, some arbitrary point here, I want to find out what is the pressure, I can just go here and say rho GH, and then this is H. Again, in my case, do I say anything? I didn't say, anyway, I just took another point. Then the pressure at that point is going to be rho GH, which is this distance. So let's see, how can I do that? So here I took an easy way out, and I took R equal R. The pressure at the bottom. We take actually this point here, right here. So I took at this point, so that's going to be easier just to prove the same thing. So we expect that the pressure at that point is going to be rho G Z max. That's what we're supposed to be, which is the answer here. Let's see if it works out. So, okay, so the pressure at R, capital R, remember, that's at the outer, the maximum radius. All I did is the little r, we put the capital R here. And this is the case. And then we just take this thing, okay? We take that. And then we substitute Z minimum from here to here. Okay, because you already have the relation between the two. And let's see, so we take this one, same equation. Instead of R omega 2, we substitute G, okay, G over that, okay, Z max minus Z minimum, okay. And then this term remains, okay. This term remains. And then it comes out exactly like predicted. So one more time, we proved that if you know the shape of the surface, you can take any point, arbitrary point, figure out what's the depth, and then the simple formula, rho GH, will work. Okay, I think we can move on to the examples. Any questions up to this point? You quiet? You all asleep? 160.
No.
No, we're doing fine.
We're doing fine.
Looks fine. Okay, okay. I go on. Again, I'm alone here, so I don't know if you guys all listening or not. Let's do examples. Let's do some examples. So let's see how it works. So I just took the same picture before, and we have a container with the full height of the container. So this is the full height, and it's 0.3 meter, and its base is 0.2. That's the diameter. Let me be careful. Okay. Pen. So it's 0.2. And then a container is spinning as a solid body, and then an RPM, 200 rotation per minute. And because I think the picture doesn't show it, but this thing is not there. It's not there. So the container is this. So it's full with liquid initially, then I'm spinning it at 200 RPM, and then some of the water is being lost. So the question, how much water was lost? And once it's spinning, what is Z average after it stops spinning? One more time. The container is full with liquid, or water, let's say water, it's water. The height is 0.3 meter, 30 centimeters. We're spinning it, okay, a shape which is described develops, which is a parabola. And then we stop the spinning, and of course now we have less water in there. So the question, how much water we lost, and so forth. So very simple, because we're looking at the condition, and maximum Z is this, because everything else was spilled. The Z minimum is at the center, at the origin, where R is equals 0. And we know that Z0 actually splits those two, it splits that distance, is exactly in the middle. So if we can find out what's the difference between Z max and Z0, which is R omega squared over 4G, then we can find out this quantity. And then what it is, okay, so R, remember the diameter is 0.2, so the radius is 0.1, okay? This is 0.1. 2 pi is 2 pi, we cannot do much about it. Rotation, 200 RPM, but it's per minute, so we need it per second, so we divide by 60. And then G is 9.8, I put here 9.8 times 4. And if everything went well, this is the answer, 0.11 centimeter. I mean 11 centimeters, 0.1. So Z0 is simply what I did. I put 0.3, which is 30 centimeters minus 11, 189 meter. And the volume of the spilled water is pi R squared multiplied by this quantity, which is 111. So here you go, pi R squared, R is 0.1, height is this, 4.5 liters been lost. Okay, so this is kind of, this was actually one of the exams in the past. It shows what can we do with this kind of algebra, and it's very, very simple. If you understand what we're doing, everything is going to be clear. Let me just go back. So one more time, you need to know the equation. You need to know these two quantities. I touched the mouse. It's going to jump. Okay. You need to know this. And then you need to know the pressure, which is the previous one.
Right.
You need to know this equation, okay, this one. And then this is the interface. So you have these three equations which you need to remember. 1, 2, and then the third one is here. the second. So that's it, very, very simple. I believe I have one more example. So we did that one. Let's do one more example. So you may ask, what can one invent for exams or something like that? So here's a YouTube, not the YouTube, the music, but the YouTube, the water. So let's see why can we claim that it's comparable? So it is filled with liquid, it's horizontal, it's not spinning. And then we can claim that there is an axis of rotation here. And if it's spinning, then probably this will go down and this will go up, and it will obey the same rules. That's what we think. Okay, so if this is the case, then the next question is what will be the pressure here and what will be the pressure here? So virtually, we have to get this Z. This is going to be the Z for that point. You can look at it any way you want, but the pressure is going to vary with the radius. So you can take the equation as is, or, okay, so let's just do that instead of discussing. So one more time. This is the axis of rotation. Okay, so YouTube, the water height is 0.2 meter, that's 0.2, and the radius is 0.3, this one, 0.3, and it's spinning at 50 RPM. Calculate the pressure at point A and point B. Okay, so point A. So we claim that that formula has all the information. Okay. So point B is, we're looking at Z max minus Z minimum. So we think that here is going to be Z max. So this is Z max. Okay. And we're just trying to find out what is Z max. So what I did here is just plug in this quantity, just the difference between the two. And of course, R, 0.3 we said, 2 pi is 2 pi, 50 RPM, 60 minute, 2G. And it gives me like 13 centimeters, 12 and 13 centimeters. That's what the distance. So this represents the whole distance between here and here. Okay, so we know that one. And therefore, if we know that 1/2 of that is how much it will rise compared to the initial condition. So we have to take, the pressure is going to be rho GH. What is H? H star, which I call H star, is this. The height in that tube, the height of that tube. The height in that tube is going to be equal to 0.2, okay, which is the Z minimum, okay, Z minimum, and times 1/2 of the difference, okay, so, or actually, sorry, not Z minimum, this is Z average. This was Z average, or Z0, plus 1/2 of the difference between the two, okay? Are we good? So therefore, we know that the height, we can use the simple formula, rho GH, multiply, and here's the number. That's the pressure at point B. That's the easiest point, okay, point B here. Now, let's see point 8. So point A, we treat to find out what is Z minimum, okay? So we find Z minimum, which is the center, okay? This is Z minimum. Okay, we found Z minimum. This is the distance. So, but the radius is actually 1/2 of the distance, which supposed, so it's 0.15 meters. So we need to take the general formula. So the general formula is this. So rho, water, 1,000. We take the radius at that point, point A, which is only 1/2, 0.15. This is the rotation, okay, in half, referring that one. And then Z is actually 0 because we are at the bottom. And then Z minimum, we just calculated it somewhere, we calculated right here, right here. So we plug in these numbers and here you go. So at the base, yeah, and then what is the pressure there? At the base, what am I doing here? Oh, I'm trying to do this point as well, I believe. Anyway, so at this point we finished. Okay, so we did here. I tried to do something else. Okay, so that's the case, and I think that's the most complicated problem that we could invent. Okay, let's move on. And this is really the main part of that particular chapter. So before we did how the pressure is changing with the depth in the liquid, rho GH formula, you know this from high school. Then we invented a case when the fluid is accelerating, but in a sense it's the same as the gravitational force. And it was really just to show how you place the body forces in the equations. So very, very simple. Now this part is actually far more important for engineering because now we're going to find out how a force is generated by the pressure term, okay? So I don't have a headline, but it's, okay. So we're looking at pressures on a surface. Okay, so here on the right-hand side, let me get again the pen before it jumps on me. So the general problem is we have an object which is inside a liquid. There are forces on it. And then what are the forces? We already mentioned that the force is, the delta F is the pressure times delta S, the area or ds area. But we also need to look at the normal. This will be the normal of the surface. And then if we have a coordinate system, let's say this way, then we have to take the projection into that direction. So I only mentioned that one before, but we're going to repeat that. In this particular case, the pressure is varying. So the pressure is increasing with the depth, okay, which I'm showing in this particular figure. So pressure is changing with rho GH. Therefore, the forces on the side are changing as well, while the forces on the bottom, if we take it just a simple rectangular shape, I run out of luck here. So if we took a simple rectangular shape, then on the bottom, if it's the same depth and it's flat, then the forces are going to be the same, which is PA plus rho G8. So very simple. I don't know why. I already, I'm having problem with this thing. Okay, I'm back to normal. So we shall try to investigate how to get the force. Now, what are the issues? The issues are the shape of the surface. And it's a strange surface. It's going to make it very complicated. So for our case, just to prove the point, we're going to use flat, straight surfaces like it shows here. It could be inclined, but we're not going to make life too complicated because we're trying to teach you the principle and not really mathematics. Although we have to use mathematics, unfortunately. Okay, so let's continue. So hopefully you understand the problem. Let me just go one step ahead. Suppose there is a pressure distribution on the side of this container, then what would be the force acting to this direction? So relative to the liquid, the normal is pointing outside of the surface, but the force is going to be here. So therefore we have a minus sign, if you recall. This is, I'm trying to sell you that equation right here. Okay. So pressure changes rho GH. And then the forces, we have minus because the force is opposite direction than n, the vector unit normal, which is pointing outside of the surface. And if you would like to find out the forces on everything, on the whole surface, unfortunately, you have to do an integral. Okay, so far, nothing new. Let's go back. Let's go to the next one. Okay, so before we go, I took the force, that equation before, it was P and ds, but instead of pressure, I put PA plus rho GH, which is how the pressure changes as we go deep inside the container. And then just to continue more about this little n guy, let me get the pen before my luck goes away. I just want to talk a little bit about the normal. So suppose I have a surface, which this is the surface of the area. Okay, now this is the same story we had with the flux. And then the pressure is going this way. So the force is going to be that direction. But the component to the x direction is going to be basically the cosine in vector form. Okay. Which I'm showing here. So the force, but nx times sx, you can also claim that this is acting on a projection of the surface, which is going to look like sx. So there are several ways of looking. It's the same thing, same answer, but could be slightly different. Also, if I have a coordinate system, which is this is x and maybe sideways is y, and up is going to be z, then I can show that ds is actually going to be this. I already incorporated here because fx is going to be the surface on this. So this is going to be z, and this is going to be y. X. Okay, y has to be the other direction. I tried to figure out the right-hand rule. This is y. Okay, so this is just those engineers that want to do a very quick estimate. You can look at that diagram and figure out what is the area projection and what is the pressure, the average pressure at that point. And you can get the force right away. We're gonna somehow make it more official. We'll do it a little bit more official. So let's do a case. So far I try to describe general rules and some suggestions. Let's look at the practical problem and try to go and solve it completely, and we can have examples on that. And this is a pretty good example for civil engineers who may do a pool design, or sometimes you have windows in those pools, and you really don't want those to break or crack. So here's the case. Okay, let's do it more carefully. First, we do it generically, and then we're going to have some examples. Because so that's the main topic of this chapter. It is very important. This is real engineering. So let's do it carefully. Let me just look at a second. How are we doing time-wise? What is that? Just give me a second.
4:45.
Just how much?
4:45.
35. Okay. Oh, okay, I'm good. Okay. I was afraid I'm running too slow because we spent a little. Anyway. Okay. Thanks for helping. I'm in full screen, so you guys can see everything. Anyway, enough talking. We need to move forward with the project. So here's the situation. We have a pool or liquid container or whatever you want to call it, and we're limiting ourselves to a flat surface. Let me get the pen. This is the flat surface of this one is a flat surface. We're limiting out to a flat surface. So it's not going to be curved, otherwise the integration starts going around, being more complicated. The depth is H, as before, nothing outside is a PA. But we're going to say in a minute that PA is also this side. So we're not going to, so delta P acting on that surface, eventually the PA will cancel. Okay? And there could be an angle. we put a coordinate system, so X is going to be into the wall, X goes in, Y is along the surface, and Z is outside, straight outside of the surface. It's kind of more convenient because now we don't have to do cosines, and the force is going to be directly to the Z direction. So this is the case we study, and this is a generic one, and will help us solve many problems which are related to that particular problem. So one more time, note the coordinate system, note the origin. Again, one more time, this is very, very important, because the way we're going to continue is that the coordinate system origin is at the intersection between the liquid level and then that surface. So I can invent a shape where it's liquid here, and then maybe it does that and does that. And then I'm going to ask you the question. So what have you do? You have to continue this surface, go to here, and then the coordinate system is going to be right here, which is not actually on the pool. And we'll see that in some of the examples. Okay, so pressure. So we mentioned this is the same formula we had before. Pressure is going to be NZ, of course, is going to be 1 to that direction, so we don't have to worry about that. And we just want to look at that because we talk about the surface in the Y coordinate system, it's along here. So the surface is in terms of Y, but the pressure varies in terms of H. So H equal Y sine alpha, no rocket science here, everybody knows that, but it's important to remember that one, okay? Remember, because what we're gonna do, some integration, unfortunately, going to be in the Y. Okay, so FZ, the force stated, is gonna be pressure, and at this point I took out the PA because of that story, the PA also acts outside. And, oh, here it is. Okay, I lost the subscript. And therefore, it's going to be rho g y sine alpha ds. Why are we doing that this way? Because ds is actually dx and dy. Okay, so there's nothing changed here, nothing interesting. Okay. Now, I have a whole convincing story here. So I'm copying the equation from the previous page. This is that. And I'm trying to figure out what is this YDS. Okay. S, of course, is dx dy. It's the area. So let's go back to something that you know very well. If I want to find out the center of gravity. So there's a coordinate Y. Sorry for my handwriting, which is very similar to what I can do with the mouse. So here's a coordinate Y, and then I have different masses on it. 1, 2, 3, 4, each of a mass. And each of them will have a Y coordinate. So I claim that the mass is sigma of all the MI, all of them. And then in order to find out the average distance, which is the center of gravity, I have to take each mass and have its coordinate added up, which is basically doing the moment. This is actually going to the moment about the original. That's what we do. And then it's equal Y average. Of course, Y average is going to be sigma mi yi divided by sigma mi. And I'm not coming up with any new discovery here. So let's look at the problem at hand. Let's say that's what it is. So I'm doing the same thing, and I'm putting Y, and I'm doing little areas, area 1, area 2. I'm just splitting the area on there. So each Y will have its own area segment, exactly like that. So along the same line, I can claim that sigma SI is equal to the sum of all the S's times some average. It's the average center of gravity or whatever you call it. And of course, I mentioned that SI is xi dy and dxi actually. And so turns out that the integral xy dy which I mentioned here, x dy, is equal to SYI. So this quantity is actually area times average y. Okay, so let's see what it means. It means very interesting. So I go back to the formula because, and it's going to make things very, very simple. This is what we proved before. So if I use that, and instead of this, I'm just going to plug in y average, then remember, this is actually h average. So what we have here is the solution, okay? So I can say that Fz equal minus rho minus G and H average, which is the pressure, times the area. This is basically, we call it P average. It's the average pressure at the centroid of the area. Okay? So that's also, instead of all these integrals, our results is very, very simple. Okay, here we go. Find the centroid of the area, where it is in the pool, and find the depth, H, or you find y average, but then you have to go through the sign thing, and then multiply by the area, have the area. Okay, so here are some geometrical shapes. And again, we're not going to use some very complicated shapes. The idea is not to use complicated stuff to make things more complicated. For example, a rectangle, center is at the center, no rocket science here. Circle is the center. Triangle is actually 2/3 and 1/3. This will be the most complicated case we're going to have. I'm going to make an example on that one, where things are a bit shifted. This is very simple, although it will require too much algebra, so I try to avoid it. But there are other cases if you're going to hit some, and then some manuals will have much more cases. This table also shows the moment of inertia, which we're going to need in a very soon, okay? So let me try to be artistic for a moment. So we have a pool like that. And it's filled with water like that. So this is water. And then you're asking, here's a shape, I'm gonna make it more abstract. What is the force on that window? So what you need to do, you find out the centroid of the area, you find out how deep it is, H, and then the pressure is going to be, this will be the H average. The average pressure is going to be rho G H average, and then multiplied by the area. This is going to be Fz, or Fz, which is normal, sort of normal to the surface. Okay, so very, very simple. We did very well here. Here is again a table which is in the book. I think this covers all the cases for this particular course. And then we're going to have an example on the triangle, which is the most complicated case that we're going to face in this particular course. Now, the more important one, center of gravity. So I have to, it's very, very important for engineers. So I repeat myself several times, but let's not forget about it. So on the left, let me get the pen again before it jumps. Again, I apologize if I don't choose the pen. I don't know if in every computer is like that. If I don't choose the pen and I touch the mouse, it jumps through the slides. Okay, so I have a bunch of bricks on the left-hand side, bunch of bricks, and I want to balance them in a little wedge. And therefore, I need to find out the resultant force. That's what the engineering called. So that force must be equal to the weight of that stock, the weight of all of them. And it's probably going to be 1/3 if it's a triangle, so we know what it is. And this is, if you put it, it's going to be fully balanced. The same story applies for a linear pressure variation. And of course, we're going to call that point center of pressure, XCP. That's what we're going to call here. Actually, my drawing should go a little bit more to the right. Doesn't matter, that's all right. So here's an example how we found it. Now remember, on the side of the pool, the pressure really changes like that. So this is very similar to what we need to do pretty soon, okay? So, okay, so first of all, how the pressure is varying. The formula for this thing here is Pmax times X over L. So the moment it will reach L, then it's going to be equal to Pmax. No rocket science here. Fz is the pressure times dx. So I just substitute this formula, Pmax out of L, and then x dx, and multiply it, x is going to be x squared over 2. X squared over 2, and then it's going to be L squared over 2 divided by L, so L Pmax over 2. That's it. So what it is, this is the pressure, which is going to be equal to, this is 0 here, this is here. So the average pressure is actually 1/2 of the maximum pressure, okay? Yeah. Yeah, multiply. This is, okay, I'm just looking at the unit. This is per unit width. Okay, what we did is per unit width. So then if we try to get the center of pressure, we have to take the moment about this point, about the original. Again, statics, you all had A in statics, I know that, I double checked. And so what you do is you say the forces due to that pressure distribution will be balanced by the resultant force, and tell me what is the distance where this average force is acting. That's how the statics goes. And this is what we're doing right here. We're saying that this average force, which you already calculated, which is here, times this XCP, which you don't know what it is equal to the same integral we did. So it's going to be X and P, and so we're going to end up with X squared. Okay, because this X, and then the other X is this one. And we end up with this quantity, and it shows a center of pre. I will just divide this by that, and we end up with 2/3 L. So that is going to act here. My drawing wasn't very great. This is acting at 2/3 point. It's not here actually. Okay, so you've done it before. So let's go back to our case. All right. So now remember that was the problem we started with, and this is the problem we're trying to solve. So far what we did, we said, okay, so here's this one is a projection. This is a projection of a surface, which is here. So the first thing I said is find the centroid. So the centroid is probably here, and then find the depth of the centroid. Again, not so accurate. So this would be H, and we call it H average. And therefore, the pressure here is going to P average. P average is going to be rho G H average. Okay, so we know that. We already know that. And then the force is going to be equal to the pressure times the area of the surface. We did that before. So now we need to do the same exercise we did before, but we're assuming that the shape is not necessarily simple. So we need to actually do integration, which is ds is going to be this. This is the ds's, we know ds's. Okay, so remember fz we already know, fz we know, and fx. So fx is we have to have y, because we're moving around the coordinate. Before we did x, and then we have to plug in the pressure. This is the pressure. Instead of y, we do instead of h, we do y sine alpha, and then ds. We're not specifying dx, dy, but we end up with this integral. So it's very similar to what we ended up before, but the integral y ds turned out to be the center of gravity, or the centroid. But jumped again. Okay. So what we do is we have fx, which is fx was equal to rho g sine alpha multiplied by y ds. We just divide one by the other. So we had fx, and then we divide one by the other, and we end up with ycp, center of pressure of y. And turns out, without really going to solving these quantities, we end up with this. So this was basically y average s. We did that before. And turns out that this is actually ixx, moment of inertia. Again, this is not fluid mechanics, this is dynamics. Okay, so that's the moment of inertia. Therefore, we conclude, okay, now you have to look at that, and then you have to take the moment of inertia of that surface about this axis. Okay, and therefore, this is how you find ycp. Now, ycp, if we think realistically, so this is the centroid of the area. Before I had the area, okay, let me just redo that, because this is very important for you to understand what's going on. So this is the reflection of the area. This is the centroid. And we said, okay, we know how much is the pressure at the centroid, but then the ycp is actually going to be further down. And the reason is that more pressure is acting on the lower surface. So we definitely need to figure out what is the moment of inertia. Okay, it's not as simple as it sounds. And then you can do the same thing on the y direction, or we did the y, which is along the plate. To the sides is x in this coordinate system. So we did exactly the same thing. So instead of y, no, pen. Somebody has to remind me to take the pen all the time. So instead of y, I put here x, because now we're doing sidewise. Same thing, exactly the same thing. So we end up with xy ds. What is this integral? This is the mixed moment of inertia. Okay, so we didn't even solve that. We just go to comparing that with fz, and then we end up with this quantity. So now we're trying to figure out what is this. I mean, from dynamics, this is the mixed moment of inertia. Okay, so if we substitute that to our finding, then xcp is mixed moment of inertia divided by average ns, and ixxy, that's going to be the ycp, which is the, now let me just say something here. If I'm looking at this is the y, which is the depth thing, y, and this is the x, which goes to the side. Actually, I think it goes the other way, it doesn't matter. Let me just get the x right now. And then if I have a very nice symmetric surface, and this would be the area, then the mixed moment of inertia is going to be 0. You remember that from dynamics? If this is a strange shape, then the mixed moment of inertia is not going to be 0. It's very much like you spinning. Again, right now we're spinning it here. So if I spin a circle, an exactly good surface, let's think about spinning something about this axis. If we're spinning it, then there's not going to be side force. But if this is not balanced properly, like it has all kind of shapes to the side, then I'm going to have, due to the rotation about the x-axis, forces to the side. That is the reason for the mixed ixy in dynamics. Okay. In our case, it is going to shift the center of pressure sideways. That's all. Okay, how are we doing? We have a few minutes left. Okay, so now this looks a bit complicated. So hopefully we can simplify it. And this page actually shows how to make things much easier to work. I already established a kind of a simple system to generate the force. So figure out the centroid, figure out how deep is the centroid, get the pressure at that depth, multiply by the area of the force. Hopefully we can do something very similar in order to calculate the center of pressure. So let's go back to dynamics. So you have these coordinate systems. Okay, the coordinate, remember, y goes along the depth coordinates on the surface. And then this is the centroid of that area of interest. Again, I'll take the pen before it jumps on me. So this is the area of interest here. And it has a centroid, no problem. We calculated it. And now we're trying to spin it about these axes. But if you look at most of the handbooks and all of them, they will give you moments of inertia about the centroid. So now there's a theorem of the parallel axis, okay? That's a theorem, you learn it in calculus. And the theory there says this: you can move those by a distance, this and this, by using that equation. This is a theory from, I'm pulling it out from your calculus from Kreisig or one of those books. So then I remember we have the previous equation. Let me go back. We have this. So pen. So would be nice if I can plug in here instead of the moment of inertia about the axis. Remember, the axis is hooked up to the interface, or where the surface line cuts the origin, or the y coordinate. That's where the origin is. So if I can plug in the moment of inertia about the centroid, which is supplied in all the textbooks. So then I have to use that one. I substitute that into that equation, and I end up with this. Pen. I end up with this. A much more friendly formulation is this. So what it means is that, okay, please tell me where is the centroid. Then the shift down is going to be this. This is YCP, so it's going to be a little bit more. And then XCP is going to be shifted this way. So it's going to be shifted outside if there is more area to this side and more pressure, or inside, could go whatever it is, okay? And that's the whole science. That's the whole science. So it's very, very simple. Let me see if I have a summary. Okay, here's a summary. So we have a flat surface, okay, a flat surface. And if we get the pen, the surface is flat. Remember, the pool could have a shape like that. And maybe this is not here, but I still have to put the coordinate system here. And then maybe I have this shape here, okay, as before. This is the shape. So here's what I have to do. Find the centroid. So I find the centroid from the textbook or whatever. Okay, so if it's a rectangle, it's naturally the center. If it's a triangle, the 2/3. Okay, then find the moment of inertia about these axes, this and this, or the mixed axis. So we did IXX and IXY. Okay, about the centroid. Okay, and then you really have to find out what is H, what is the depth, if you know what is Y. You have to work with Y because that's in the equation. Remember, Y is here in the equation. So you need to know that one. Sometimes the problem is given with Y, and then you still have to figure out what is Y average, because that's how the formulation is given. So this formula is very simple, but you have to remember that. Once you know the depth, you find the average pressure at the centroid. Here it again just says what it is. Force is going to be equal to average pressure times the area. And then the shift to the side, if it is not symmetric, one more time, if the area, this area is not symmetric about that axis, okay, not left and right is not the same, then Ixx is not going to be the zero. If it's symmetric, it's going to be zero. Otherwise, for symmetric bodies, some of the examples we're going to do, the shift down is going to be this. So the same table, you find out what is the area and where is the centroid, you find out what is the moment of inertia. You know what is the area, y average, you just calculated with this formula. And that's very straightforward, very, very, very simple. Any questions up to this point? I think I can come back with examples which will clarify, but I want to make sure that the process is very, very simple. This is all we're going to do, okay? Because this was all the footwork to develop the simple approach that can help us to solve practical problems. So, okay, any questions? I'll get out of share. Any questions up to this point? I don't hear you.
I think you have a question in chat.
Sounds reasonable or so far? And we're going to do examples today. We almost finished the class, so I'm not going to do examples today. We don't have enough time. But again, this process made it easy to solve practical problems. And we're going to do it next time. I hope that the presentation, I try to make it as simple as possible, and it is really simple. Yeah.
There's a student who asked a question in the chat asking if on exams, are you going to make us derive these equations or simply use them?
Where is the question? Okay. Somebody's eating. Okay. That's fine if you're eating. You can show it to me if what you eat. I mean, I'm hungry too. Okay. I think I said that, and I'm going to say it again, and you're going to ask it again. I'm going to do examples, okay? And the homework and the exams are going to be along the examples. It's not going to be difficult. So in this particular case of today, I had to go through the algebra, through the integral. I know you love that. But at the end, we developed a sequence which is very, very simple. And then we can apply that to practical problems. So you should be able to solve what I'm going to do next, okay? And then you should understand what I did so far. But I'm not, okay, so let me give you an example. If I now want to be a fancy professor, I'm going to tell you, please develop the same case for a curved surface when the surface is curved as a parabola. What all this will do is just will change the integral to a far more complicated shape, and which you should be able to do, but this is not the objective of this course. We're not trying to make a mathematician out of you. We're just trying to prove the principle. And this particular chapter is really emphasizing the forces due to pressure, and then the concept of center of pressure, which is super important in engineering. Mm-hmm. So these are the main topics, and I don't want to waste the algebra, too much algebra, and not focusing on the main point, which is really these things. Okay, are you guys?
Thank you.